Before jumping into the topic of how industrial IoT changes this paradigm of controlling energy systems, I think it's a good starting point to a bit define IoT, at least the context of this presentation, because there's a lot of debate about what IoT actually is. In the industrial space, it comes with this 4.0 revolution, where we start seeing a lot more machine-to-machine communication. We start to leverage the power of sensor data for different applications, from predictive maintenance to better control to optimize production, whatever. That touching also on big data technology and machine learning, that again, to facilitate these process optimizations. I'll first touch on how traditional operational control was done for energy systems in the good old days, when you would have these centralized power stations. Mostly they were coal-fired, nuclear or hydropower plant, and they would have this national energy dispatch center that would be informed of the production at each facility. And from this national dispatch center, a country would control its energy generation. Now, these facilities had some specific characteristics, because nuclear power plants usually provide an energy baseline. Once you powered on one of these nuclear reactors, you couldn't just switch them off whenever you want. You'd need to have them running for months. And usually once you powered on a nuclear reactor, you do not want to stop it. It would be a very costly operation. You would have hydropower stations for the countries that have running water. Now, those have a tendency to depend a lot on the water level, if it rained or not in that year. So they're not very reliable to do control, as they depend on an external factor. And usually control would have been done with these coal-fired power stations, where if you needed more energy, you would just throw more coal to burn, heat some water, and with the steam to make a turbine spin. Now, they were very mammoths, I would say, that would move rather slow. But in those days, it would be very predictable how much energy you would consume at what point in time, immediately in the morning or late in the evening when people would come back to work, and you would know pretty much what facilities you would have around the country. Now, control was done manually, and it still is for very critical systems. And you have these analog systems that are sent to the control room. Wanted to mention that in recent years, they've started being digitalized, meaning that we see these SCADA systems, SCADA standing for Supervisory Control and Data Acquisition, and DCS, which is Distributed Control Systems, using these PLCs to take sensors, read the data, have a control logic on them, and then through actuators, manipulate the process in the desired state. Now, this telemetry would be collected through dedicated communication loops, meaning either a dedicated communication line like fiber optics, it's a good example. Or if you would go to radio, either dedicated bandwidth channels, dedicated channels, or if you would use a mobile operator, you would have a dedicated APN. So pretty much trying to keep the communication link as closed as possible from the outside world. Now, what changed? First of all, we've seen a very high increase in energy consumption in the last year. Factors starting from the electrical switch and transistor. The transistor was made in the 50s. Then you see when the smartphone came into place, blockchain consumes a lot of energy to do those hashing, ridiculous amount of energy, which although the algorithms exist for some time now, they were not feasible from an energy point of view until now. And we have electric cars and this constant transition, even when it comes to heating, to look at electricity and switching and shifting from gas. If you look at this graph at the end of 2021, you see going down a bit, which was the COVID crisis, and then it went up again. I'll not debate what kind of fuel we're still using to generate energy, but oil and coal are still very important at a global scale. Now, how it looks today, and this was to present a bit the background and look at the current situation of energy systems and touch on where industrial IoT comes into play. Now, besides those, what we call them bulk energy generation systems, we start seeing these microgrids. What this means is you start having solar panels on a house. That solar panel produces energy for the house itself, but can also be sent to the grid. It can power an electric vehicle, and some future applications can act as a battery to balance the consumption. We have wind power in certain cities, in towns that provide energy locally to that town with its own energy storage. Now, the picture changes a bit because you don't have just those traditional sources of power. Now you have a lot of wind and solar distributed across the country. And naturally happens this transition towards distributed energy systems. Now, why this poses a challenge from a control point of view is that now you don't have one facility. You need to do fine-tuning control across multiple locations that might or might not be standardized. And this was not possible until recently with the adoption of industrial IoT. Now, also why we need this control a lot is about the fact that although demand is on a constant rise, it fluctuates a lot. Take, for example, holidays, this tendency to work from home. You don't know exactly where there is a load in a city anymore. It's not that predictable as it was in the past, and now you need to have a lot of live data and adapt to the situation. Now, one other important fact about this transition towards the distributed systems is increased security, because now we don't depend that much on these high power stations. We can create islands of self-sustainable microgrids. So a town in itself can be self-sustainable from an energy point of view and just require a bit of power from the national grid. And in case of blackouts or any major event, they can become isolated and reconnect a lot easier than the whole process of powering on a country after a blackout, which is very complicated. Now, the challenges and solutions, well, these are from the perspective of optimizing cost and improving efficiency. So keep in mind that industrial processes are designed for this 25-year life cycle, whereas IT infrastructure usually are designed for 5 years. Realistically, the process is good for it to be designed for 25 years. Once you've built something, you want to keep it running. But from an IT point of view, you just care about the data. You just want to take that data out of the process and either aggregated values of how much it produces or different parameters or raw data so we can do some analysis on it. So this is important to keep in mind that we just want that data to be taken out and put in a data lake somewhere. Utilities, for them to build their own infrastructure can be very challenging in this constant changing technological landscape, but also in a very competitive job market when it comes to IT tech and tech talent. And it's not necessarily their activity. They just operate these powerhouses, and they're not specifically trained in doing IT work associated. So as a solution, cloud deployments can reduce the operational effort of managing that data room, especially when you think about compliance aspects or general maintenance, servers, disks changes, and so on. And it makes it a lot easier to, when you migrate and go for a cloud approach, it's a lot easier to deploy new technology on the data you have there. You don't need to do major overhauls and redos. What else? Another challenge for the utilities is, again, maintaining this on-prem infrastructure. As mentioned, that is not their core business, and securing it itself can be a daunting task, because if you add the fact that it's hard to find skilled workforce on the IT side, if we're talking about cybersecurity skilled workforce, the demand way outgrows the offer on the job market right now. So something like infrastructure as code provides standardization, traceability, easier to do monitoring on a system, patching, plus leveraging all the experience from a security point of view that a cloud provider has compared to whatever your team would design on-prem. And the major challenge when looking at this increase of renewables, be it solar power, hydrogen, is doing the granular control that I was talking about previously for all these new emerging facilities. And into play comes this concept of virtual power plants, which is actually the result of industrial IoT applied to the energy sector, and the definition, it's pretty much the definition of doing distributed energy control systems. And what I mean by this is that now having this picture of, okay, for every generation site, you just have some sensors that send data to an aggregator, and that aggregator sends the data up to the cloud. Well, now in the cloud, I can create a virtual power plant to which I connect multiple power sources. And I can do fine tuning and control of how much energy is being generated in every location from this virtual environment. So how IoT plays into this is the interconnectivity part that, as mentioned, you have in one place energy generation, energy storage units. Take, for example, the home box from Tesla with the battery packs, which is a good example of energy storage units. And they all can exchange information in real time about their capacity, status, and whatever relevant data you need to control all these locations. Real-time collection of data allows you to naturally do optimization on your operations and not have something running and producing energy that you don't have any consumption for in another place, energy that you just dump. Now you can fine-tune that production of energy to an exact consumption that is located somewhere. Plus, this is really critical when we're talking about stabilizing the frequency in the grid, because you don't want to have a fluctuating frequency, because the whole chain would destabilize from generation to consumption. Plus, with these virtual power plants, you can run automated control on them. And most importantly is for the predictive maintenance part, because when you have that granular visibility into each location, you can detect in advance if something is out of its normal parameters. It might have a fault soon, and it's easier to change it proactively than after the fact when it's not generating. You're doing it outside of a scheduled maintenance window. It's a bit more complicated. So if you can fix it, detect it in advance and schedule it for a maintenance window, is the most cost-effective way possible. So just to go a bit into the key benefits of this is grid stability. It's cost effectiveness, as mentioned, that you reduce the overall operational costs. You increase the flexibility by adapting to changes in demand and supply quickly, making which is really useful in cases of power outages. You have a flood, you have a natural disaster in a certain location, and it's more easy to adapt the energy system. And again, and the most important thing is the energy efficiency. What I was mentioning earlier, that you can optimize the use of each unit and reduce the need for energy transmission over long distances when you operate in these microgrids environment controlled by these virtual power plants, as you reduce dependency on the national transmission operators. This is just like a quick overview of where this comes into play, and open to questions now or after. Sorry if the presentation was rather generic, but I think it's more useful to do a dynamic Q&A after than to go in a specific topic. So Chris, back to you.
Thanks for watching this IoTSF webinar. The IoT Security Foundation is a non-profit membership association dedicated to promoting the security of the Internet of Things. We provide access to exclusive resources, tools, and working groups to enable best practice deployment and next practice development. We help you raise your profile and offer opportunities to network with experts and other security professionals. We give you a voice in the development of standards and a channel to influence regulation. And don't forget that our members can create their own regional chapters to further extend local interests. To learn more about our mission, go to IoTSecurityFoundation.org.